Hello everyone, my name is Weerakorn Sinlapawongsathorn. Today, I'm going to show you about the BufferOverflowAttack lab. It is from the SEEDLab. So this is my first time doing this. I hope you will enjoy my video. So let's get started with the buffer overflow. What does the buffer overflow mean? So look at this one. Buffer overflow is defined as a condition in which a program attempts to write the data beyond the boundary of a buffer. What does this mean? So it means that we assume that the buffer overflow has a size of 100, but a program attempts to write data or input data beyond the 100. It could be 120 or 200 or 300. So it beyond the size of the buffer to hold the input data. This is called the vulnerability. This is called the buffer overflow, and this is considered as a vulnerability that can be used by the malicious user to alter the flow control of the program. So in this lab, this project, assuming that we are an attacker to exploit this vulnerability, because we need to learn, gain the practical insights into this type of vulnerability, and learn how to exploit the vulnerability in attacks. So we are an attacker. We are a malicious actor to exploit this vulnerability because we need to learn this type of vulnerability so we can have a picture in our minds how to protect it, how to mitigate it. So let's go through these materials together. This material you can get from the SEEDLab as well. So before we starting the actual lab, we need to look at the environmental setup. Turn off the countermeasures. Because in here you see that the modern operating system have implemented several security mechanisms to make the buffer overflow attack difficult. So it means that the system or this virtual machine that I'm working on, it has a countermeasures to protect or prevent the buffer overflow attack. So we, as the lab, it requires us to learn this vulnerability, to exploit this vulnerability. So we need to turn the countermeasures off. So let's look at the countermeasures one by one. Address space randomization. In here, it describes as to randomize the starting address of heap and stack. This one, why we need to turn this off? Because it will make us to guess the exact address difficult. Guessing the address is one of the critical steps of buffer overflow attacks, because when we need to exploit this vulnerability, we need to know about the starting address to exploit the vulnerabilities, right? But in here in the randomization, every time we using some technique to get the address, it is randomized. It is not the same as it isn't the same in every time that we run the program. So we cannot get the exact address. So it makes us difficult to reach this target, right? So we use this command. Sudo command in here. You see the zero? The zero means we are turning off the randomization. And next countermeasure, configuring bin sh. Or we can see the dash program, okay, because it prevents itself from the being executed in setuid program. Because in this lab, our target is setuid program, the setuid. So if we need to get to execute in the setuid, we need to turn it off. Because let's assume that the setuid is the victim and we are an attacker. So in here, how we can do this? This lab will link the bin sh or dash through another shell that doesn't have such a countermeasure. In this one, we link to this. You see this one, this command. We link the bin sh to csh. So it means that we link, and this time this shell doesn't have this countermeasure to prevent itself from being executed in the SETUID. So now we can get to the SETUID. And next one is a stack guard and non-executable stack. So let's talk about this. Stack guard, it means that it's a compiler. It prevents us to modify the return address. What is significant for us? For the return address, for the modification on the return address, I will tell you about this later because it's in the next few section. And for this one, the non-executable stack, it means that it doesn't allow the stack executed, but we need to make it executable. So in this lab, you will know why we need to make it executable. In here, for both of this one, for the non-executable stack, it's like the operating system marks some compartment to be non-executed, and the CPU will refuse to execute it, right? But in here we need to. But why they mark in here the stack? You will know about it. So this one is getting familiar with the shellcode, because in this lab they provide us a BufferOverflowAttack zip file, and we need to download it. And inside it has a shellcode file and code file. In here we need to get familiar with the shellcode. So let's look at this one. In the shellcode file, it's called the call shellcode. In here, they provide the 64 bits and 32 bits binary code. Right. It's a binary code is the code in here. So why they provide? We will use both of them to see how different they are. In here, so when we look at this one, you see this. We need to compile the 32 bits and 64 bits by using some command, and we need to use make to create the file of 32 bits and 64 bits. Don't worry, we will work together in this video. So understanding the vulnerable program in here, because as I told you in the BufferOverflow SEEDLab zip file, they provide the vulnerable program in the stack file. But in here, we don't know where the malicious code is, where the vulnerable program is. So that's why we need to find a way to reach it. In here, let's look at about the stack file. Inside the stack file, in here is the buffer overflow. So you can consider about this during this one. I will try to explain this code as much as I can. So look at this main function. In the main function, it contains this one, the char string, the string, right? 517, the size, the array size of the string. So it is the maximum size. And what are they gonna do? This file, they open the bad file for read, you see? And it reads the size of this one, right? And then it passes the input to the buff function. So in the buff function, it calls the buff function in here, right? So in the buff function, it has this one, the buffer size, but it's just only the buff size, which is absolutely less than 517. And then string copy the string to the buffer. So in here, you can see that the string copy doesn't check the boundary of the buffers, of the input data. So the buffer overflow can happen during this section, right? In all tasks in here, we need to create the bad file, because this is don't forget that this is the vulnerable program or the malicious code that they provide us. We need to reach this malicious code, so we need to create the bad file first. And when the vulnerable program copies the content, so string copy, right? Call the buff function and string copy to the buffer. A root shell can be reached because our target is the set ID. We need to get to the root shell, get to the root privilege. But how? So in here, let's look at this first. How we can reach to the malicious code. In here, in this picture, you see this? Because inside in the file, there has a code that provides the field the NOP operation. This is the return address. This is all malicious code. We need to reach this one to exploit the vulnerability. But how we can do this? We need to find a way to reach it. And you will know about this one, but you need to know about this, the NOP. Why is we need to create a NOP to reach the malicious code? What the NOPs mean? The NOP is no operation. It doesn't do anything meaningful, just advancing program counter to the next locations. So every time, as long as we hit the NOP, it will go to the next location until the malicious code. But before that, you see this one, the return address. We need to get to the return address. These are tasks. These are objectives to do to reach the malicious code to find a way. And now we are going to this, going to the return address and then to the NOP until the malicious code. Oh, go back. So in here we need to compile them because they provide us the file, the 62 bits, 64 bits and 32 bits, right? We need to compile it. See this code is compiled, right? In here, let's look at this command. Look at this command. -c execute exec stack. You remember about the non-executable stack countermeasure. Because we are malicious code in the stack file, right? But the non-executable make it not to be executed. So we need to turn this to countermeasure off using this one, make it executable. And this one is a stack guard. The stack guard, this one is we are turning off the stack guard countermeasures. You remember about what I mentioned about the stack guard? It prevents the modification of return address. Because we are reaching to the return address, it will prevent us to modify the return address to get to the malicious code. So we need to turn it off as well. And here, okay, you might be wondering why, because we just get to the return address, right? So let me tell you about this. When the buffer overflow occurs, so it means that the buffer, because we input the data beyond or over the buffer size, it means that the buffer size will be expanded. So what does it mean? It means that the return address will be modified because of this, right? And what happens next? When it is modified, the return address can return to the new address or new space, right? And this is what will happen, okay? The impacts of this, the several impacts. The first thing is, if the new address is equal to virtual address, not inside the main memory, so it cannot be returned. The return can fail and the program will crash because it's not inside the main memory. We need to use the program deployed in the main memory, right? But now we cannot because it returned to the new address in the virtual address. It's not in the main memory. And the second, if it's in the new address is in the physical address, but this address is utilized by other, such as operating system. So what it means, the return will fail and the program will crash again. But what if it is not using by that one, but the new address is a physical address as well? But what if the data is not valid? The data is not valid, so it means that the return will fail and the program will crash. And for the last one, if the data is valid in the physical address, but as you know that the buffer size is expanded and the return address is modified, right? So the logic of the program might be different from the original logic. So it means that the result can be unexpected. So that's why here we are modifying the return address, right? So that's why we need to turn off the stack guard, right, to make it successful. And this one sudo root, we need to change the ownership of the program to root. And this one we change the permission. CMOS, we change the permission to enable the SecUID, as the SecUID is our target. After we run this one, so looking at this, we can start with our real task for this lab to be successful for this lab, to study about the exploitation on this vulnerability. So open the terminal first. Because I have already downloaded the zip file, okay, we can work this one together. You see this one, I have already the buffer overflow. In here, so in the buffer overflow attack file, zip file, it provides us the code and the shell code. Let's look at the shell code together of this one. But remember that I told you right in here. So this one is the 64 bits and this one is 32 bits, as I mentioned. And then let's look at the stack file. Okay, this one, you see this one is the size of the buffers. Open for read, and this one called the dummy function, and inside the dummy function is the buff, as I mentioned. So okay, now let's go. Before doing, we need to compile it, right? First of all, we need to compile the shell code first to create. You see about this one, create about in here. So we will go to the cd shell code, and we will use, look at this ls. Okay, that's what it. Okay, because I have already compiled it, but you will to create it, it just is string made, and you see this, it create this one, create this, turn off the non-executable stack, right? But in here, let's look at the first task together, because in here we need to compile in the stack, right? In here, the target is in stack, and the stack is in the code, right? We need to run in the code. So go back and get the code file, and then we need to compile it. Okay, we compile this one, we use this together in here, and sudo shown and sudo cmos. But we didn't finish yet. We need to turn off every countermeasures. So let's go back to the countermeasures and use this one, turn off the randomization. As I told you that we need to get the address to access it to reach the malicious code. Okay, in here it allows sudo. Okay, and now we need to link this one to another shellcode that doesn't have a countermeasure to prevent us, because we need to get to the SecUID, right? In here. Okay. Because I have already tried this lab before, so you can see that but we will work together from the beginning, and I will try my best to let you understand about these vulnerabilities as much as I can. Okay, so let's take a look at this one. In here, to exploit the buffer overflow vulnerability in the target program, The most important thing to know is the distance between the buffer's starting position and the place where the return address is stored. Because we need to get the distance between the we need to get to the return address and then it get to the knob and to the malicious code. For the distance, how do we do this? We will know this in this task, don't worry. We will use the debugging, so we use the GDB, right? We have the source code and target, we can compile it, debugging to turn on. Okay, so debugging is at if we run make. Okay, because I'm going to line by line with I would like to make sure that I would like to make you understand as much as I can, even though my background is not computer science. So in here, let's start with this one. You need to create a touchbed file because in the vulnerable program it opens the bad file, right? So you need to create it. But in here, I have already created a bad file. But okay, you can use this command touchbed file and just enter, and that's it. Now in the level 1, we will use the stack level 1. So in here in the code, it has the stack level 1, level 2, and level 3, level 4. What does it mean? What the difference? It's different because the stack L1 means the level 1, stack L2 means level 2, L3 means level 4, level 3, L4 means level 4. Because in this video, we will cover 4 levels to understand about this vulnerability. Okay, so first of all, use shoot GDB, right? Use debugging at the stack L1 because in this level 1 we need to use the L1. Don't forget that we are loading in the code because it's stack in the code file. Okay, and you see this one in here, and we need to set the breakpoint at above. Why we need to set the breakpoint at above? As I mentioned, as I show you about the buff function, right? That call the buff function and it copy the string to the buffer. So we set this one and we run. But this run after we use the command run. It stopped before the ebp, which is the frame pointer. So we need to get the frame pointer, so we need to get to the next. Using the next command, you see this one. It will stop after the ebp. This one, the string copy the string to the buffer. So let's go to the next direction. So we will use the ebp in here. Let me have a look at this one first. I have already, okay. Okay, because in here, I'm wondering that's why it's different from the okay, first of all, let me check first. Just wait a minute. Okay, let's see. B both run next P, okay, E B P. Okay, because the last time that I did, you see this number, the serial cost FFFFCA68, because the last time that I did, I got the 78 numbers, but it's fine, because now we are doing together and it can happen. Okay, so and then we get the buffer address for this one. Okay, and then but how to calculate the distance between the buffer starting position and the place where the return address is? So in here, we will use this command, P divided by D. In here. The distance is 108. So before moving next, I will show you something. In here, this picture, this is the distance. In here, we're filling the knob, right? And do we know about this? So the distance from the starting position of the buffer to the return address. But in here, it plus 8, so you know about this. You will know, right? Okay. And next, let's go to this one, the next move. After we know this, we quit first, and in here to launching the attack. Launching an attack, we need to prepare a payload and save it inside bat file. We will use a Python program to do that. We provide a skeleton program called the exploit.py, which is included in the lab setup file. The code is incomplete, and students need to replace some of the essential values in the code. So, after doing this, we need to look at the exploit.py file. This is the exploit.py file. The initial exploit.py, you see this one in the shellcode, right? You see this. So we need to copy to replace the contents with the actual shellcode. So, and we're using the 32 bits. So we need to replace with the 32 bits. And you see this one, fill the contents with knob. So in here, you remember about this picture, filling the contents with knob. Where is okay? So it fills the content with knob, because as long as we hit the knob, it will go to the next location until the malicious code, right? In here as well, it fills the contents with a knob. And this one, the starting, okay, the starting position. Put the shellcode somewhere in the payload, okay. In this case, we will use this the maximum size minus the length of the shellcode. Okay, for this one, for the red means the return address. In this case, we will use the EBP. Okay. And the offset means the distance that we calculated, the distance between the buffer starting position is 108. But in this case, we need to pass 4. Why we need to pass 4? Because because the size of the return address is 4, right? So we need to pass 4. Let's look at this together in here. Once the input is copied into the buffer, the address of this position will be, and this one plus x, y plus x, because it depends on the length of architecture as well. So in here, but we pass 4 instead. So 108 plus 4 means 112. And this one is the length you consider about this. L equal to 4 is the length of the 32 bits address. But it will be 8 for the 64 bits, but in this case we will use 4 because it is 32 bits. Okay, and then I forgot, I need to copy this first. Okay, copy this into this, paste it, and save. After that, we need to check it. Okay, so after that, we need to look in this. We need to run the exploit and stay one. We are running our malicious to get to the malicious code. Okay, we use this exploit.py and stack L1 equals the segmentation fault. What does the segmentation fault mean? It means that this one is pointing to somewhere, not the return address. We need to get to the return address. So what should we do? We pass this one. We pass the red means return address. Don't forget about it. We need to pick up the number, and we will pick up at 100. Why I pick up at 100? So I will show you. Look at this one. Okay, here for the instructors customization, because I saw this to make the website different from the one offered in the past. Alright. But in here, instead should pick up the value for this variable based on the. Okay, you see this one. The smallest value is the 100, so it should be like a 100 at the initial to classes. So that's why I select 100. So with 100 and save, and looking together the same thing, the trace, and so oh, you see this? We can get to the root shell easier use by passing the 200. Let's see, let's assume that let's see 150. Why we need to reduce this one? Because we need to get the exact number. We want to get to the smallest one. Okay, irregular instruction. So the smallest value is 200. And we get the root shell. So our exploitation is successful. Then while it's not immediate, so we have already reached to the malicious code, and we get to the root shell. Okay, now let's go to the next task. That way we are going a step by step, because I understand that you might not like have a backup of IT or something. Me too. So that's why I'm trying my best. In L2, so this one, level 2, the task 4. Let's read it together. In the level 1, you see the GDB because we get to know the size of the buffers. In the real world, this piece of information may be hard to get. So it means that we may not know about the size of buffer. In the general message, we will not be able to get a copy of the mail. In this task, we are going to add a constraint. You can still use GDB, but you are not allowed to derive the buffer size from your investigation. Actual buffer size is provided in Makefile, but you are not allowed to use that information in your attack. So we don't know the size of the buffer. We don't know the size of the buffer. And even your task is to get the vulnerable program to run your shellcode under this constraint. We assume that you do know the range of the buffer size, which is from 100 to 200 bytes. So in here, we do not know the size of the buffer, but we know the range of the buffer size from 100 to 200 bytes. Another fact that may be useful to you is that due to the memory enlargement, the value stored in the frame pointer is the EBP, is always multiple of 4 for 32-bit programs. So in here, this condition is different, and for the level 2, we are using the stack L2. In here, we don't know about the size of buffer. So what we're gonna do, the solution that we can do is we can spray the return address right to here. You see that the override space, we assume we don't know about the size of buffer, so we don't know the ABP. So keep the BP out, and we only have this one. We need to just spray the return address. What happens when we spray to the return address? When it reaches to the actual return address, it will override the actual return address, so we can get to the malicious code. Because right now we don't know the size of buffer, so we need to spray it with the return address everything when is not the actual return address, it means that it's nothing, right? But when it reaches to the actual return address, it means that it will override the actual return address. So how are we gonna do this one? Okay, first of all, let's run the GDB on the stack L2 first. Okay, B both run next and P edb okay, I use the wrong thing. Okay, you see that the P ebp is the same thing that we got right from the level 1, so it means we turn off the stack, we turn off the randomization. So and then we buffer. Okay, but in here we don't know the size of the buffer, so we'll skip the offset. And now we got this one. So look at the exploit.py. Because we don't know the size of buffer, we cannot use the ebp. We will use the buffer instead, the buffer address in here. Paste it, and this one we use. But because we don't know the size, so we cannot know the offset, right? We don't know the offset, so we leave it as a comment. So now it means nothing. And to spread the return address over the buffer, have you considered about this? The content of this one, the offset plus L equal to return address dot 2 bytes. Okay, we can use it. We can use this in the offset. We can use the Python code for. We will use the loop for the offset in the range of 50. Why I use 50? Because the range is 100 to 200. So 200 multiplied by 4. The 4 is the length of the 32 bits, right? So it's equal 50. And in here, we need to indent. And do you remember about this one? That they told us another fact that may be useful to you is that due to the memory alignment, the value stored in the frame pointer is always multiple of 4. Multiple of 4 means the length of the 32 bits, right? So the offset should be multiplied by 4, and here multiplied by 4. This one is multiplied by L. There is the length. So and save, and now we're gonna run again. So we use the exploit.py command and the stack L2 command, the segmentation fault. Let's go to the 200 irrigation. It's still segmentation fault. So let's go to the 100. So now we can get to the root shell with the value of the 400, but now we need to know that it is the smallest value or not. Okay, in here we need to try to use it 350 because it's in the middle. So it means that the smallest value to get to the root shell, to get to the return address and the root shell is 400. See, in here. So now let me conclude this one first. So level 1, we know the size of the buffer, right? We run about the exploit.py to get to the return address and then to the malicious code until we can get to the root shells. So we run the vulnerable code using the stack L1 and trying to find the exact address, right? Using the red in the exploit.py file here plus the number. But in the level 2, we don't know the size of the buffer. We only know the range of the buffer size from 100 to 200 bytes. One solution is to spread the return address to get to the actual return address. What we gonna do? How we gonna do this one? So we spread using this for loop, the Python code for loop, right? In range of 50. The 50 means that 200 divided by 4. The 4 is number 4 is the length of the 32 bits. And this one, the content of offset is multiplied by length, because as it told us about the fact about the frame pointers, it multiplied by 4, right? The value stored in the frame pointer, so we multiply by 4. So let's go to the next one. In here, launching the attacks on 64-bit program, level 3. Now we are using different architecture. Let's see, and using stack L3. It means that the L3 is the 64-bit. We will launch attacks on this program. The compilation and setup commands are already included. Similar to the previous task, detailed explanation of your attack needs to be provided. Okay. So the similar one with just the similar period, so it means that the period is level 1. Why period to level 1? Because the level 1 we know the size, and in here as well we know the size of the buffer, but we're using different architecture. So we need to change the exploit.py code. Okay, in here we change this one to be 64-bit, and we need to get to know the frame pointer, right? Frame pointer address. Okay, TDB on stack 3 and B both. Run. Next. Okay, and using PRBP. Why we're using PRBP? Okay, in here the tool is architecture. Using a TDB to conduct the is the same as that on the 32 bits. So investigation on 64 bits. The only difference is the name register of the frame pointer for the frame pointer. In here, the frame pointer of the 32 bit is ebp, but now the architectures of the 64 bit is rbp. So you use rbp. So you see this one is larger. It's longer and larger, right? So it means that it's much more difficult, but we will see it together. Okay, MP buffer. But I want to tell you that the RBP and EBP number is different from what I had done before, but the step is the same, like because like the level 1 and level 2, the same EBP, the one that I did before, the same as well. Okay, but I don't know, but it's okay because now we are studying together. We need to study about this vulnerability. We know how to use this, right? Okay, we need to see this one. How's it to calculate the offset? Okay, but the offset is the same. Okay, the same, I mean like the same that I did before. So in here, 208. And now we're gonna use this one. You see the RBP. And change this one to 100. And we need to get it back to the previous one. Get the offset back using the 208 plus 8. What is plus 8? The range, you see this one, the range of the 64-bit is 8. So we need to pass 8. The size of the return address. In here, we get to the original one. This one. So we will see how it works. But in here, 208 plus 8, it means that 216. And then let's work together. SLD segmentation fault. So we need to increase this. Right now 400 segmentation fault, 500 segmentation fault again, so 600. Segmentation fault again. So it's now almost 1000. We know where it will be stopped, right? So 1000. So you see that how difficult it is, right? It's difficult because it's architectures, and can you do you remember the longer address, right? So now it's difficult. Now 1400. 1500. Don't worry, I'm with you right now, okay? We will work together. Here, 1600. We get to the root shell. But let's see this. We need to get to the smallest value. So the smallest value is 1550. It's more difficult, right? Due to its architecture, so it's too rational, so it's difficult for the attackers to exploit this one, but it can be. It is possible. Let's see this, the challenge. Compare the buffer overflow attack on 32-bit machine. Attacks on 64-bit machine is more difficult. The most difficult part is the address. You remember that the address is longer. Although the 64 architecture supports 64-bit address space, only the address from 0.00 through 0.00007 blah 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 is allowed. That means for every address 8 bytes, the highest 2 bytes are always zeros. This causes a problem. Why is causes a problem? Because in here we need to store at least one address in the payload, and the payload will be copied into the stack via the string copy. We know that the string copy function will stop copying when it's 0. If C is 0. Therefore, if 0 appears in the middle of the payload, if the 0 appears in the middle of the payload, the content after the 0 cannot be copied. So this one is a challenge. Right? We need to make sure that we don't have a 0 right in the middle. Okay, you can see that's one. So I can conclude that the 64-bit is much more difficult than 32-bit due to its architecture, due to its the address. Okay, now let's go to the final level. In this here, the task C, launching attack on 64-bit program level 4. The target we use the stack L3, AMC L4 in this task is similar to the one in the level 2, except that buffer size is extremely small. We set the buffer size to 10. So what does it mean? So within the size of buffer, we set the buffer size is 10 within the size, right? Our code is the same. Getting to the root shell by attacking this setuid program. You may encounter additional challenges in this attack due to the small buffer size. If that is the case, you need to explain how you solve those challenges in your attack. So let's work together. Now we are going to the stack L4. We need to run to get to the address in here. We use the gdb stack L4 again. Be both run next p rbp. You see that it's still the same, right? rbp is the same, right? And p buffer. But now they set the buffer at 10. We set the buffer at 10, so we know the buffer size. So, but we will use the buffer address for this lab. Copy in here. We know the size, so the offset is 10 plus 8, 18, right? And this one, let's start with the 100. So let's run together. Let's work together. Be patient. Segmentation fails. Let's see. Even though the size is smaller, extremely small, but it's still difficult to get to the root shell. It's about 1,000. Now it's 1,000. $200. Oh, so you can see that we can get to the root shell with this number, but we need to find the minimum value. So let's try this. Okay, so the smallest value is, the minimum value is 1,350. So you can see this one. Let's compare to the level 3 because it's the same architecture. Okay. Meanwhile that while we were doing the level 3, you can remember that the size is too large, 1,550. But in here, 1,350. Even though it's just like a 150 difference, but we can see that it can get the root shell easier than the level 3, right? So the size is another indicator for the exploitation. For the exploitation, like the vulnerable to the easier exploitation. Even though it's still difficult, right? Because it's architecture. So in here, now we can get to the root shell. We can see about what it is about the architectures because the size is too small, right? So right now we have already covered all the levels of this lab. I hope that you would enjoy my video. I try my best to explain it. I would like you to understand about this vulnerability, about to get to the objective of this study. So you can see that the different architectures. So the higher architectures, the harder exploitation. The smaller size, the easier exploitation is. When we compare this one, and we demonstrate about the different methods that we use in level 2 and everyone you can see that when we know the size and we don't know the size, so the difference methodology in here. Okay, I hope you enjoy this one and try my best. My background is environmental engineering, not computer science or programming. It's my first time studying this and doing video. I hope that you will enjoy about this. And for me, this lab is very beneficial for the newcomer to the cybersecurity because we have no background. It's better to understand the vulnerability why we need to protect it. We need to apply the attacker's message for the mitigation strategy. In here, how to how to mitigate this buffer overflow. We have stack guard countermeasures, we have the remediation, right? But we can use something to check the boundaries of the input data, so we can avoid the buffer overflow. So this is what the objective of this study, because we would like to study about the vulnerabilities. We need to learn how to exploit, to understand about the concept of it. I hope you enjoy my video. Thank you so much. I appreciate it. Thank you for your time and consideration. Thank you for watching.